All right, so day, this is day O2, not AB02. You said number one, you said? One? Number one? Number one. The point in the curve, x squared plus 2y, nearest the point 0, negative 2 occurs where? Y is. All right, so this is a optimization question. And if you remember, whenever we're trying to minimize distance or maximize closeness, this is where the endpoints are relevant. They could be the answer. So the first step is to draw the picture. So if you solve this, you get 2y equals negative x squared, and y would equal negative x squared over 2. So that would be the graph of the parabola. So let me kind of draw that. Looks like this. There it is. And the point 0, negative 1/2, I'm just going to draw that right there. So if you're thinking about an interval where it might live, it could live in here or it could live in here. And somewhere in between would be a viable point as well. But if it's beyond this point here, down the parabola, it's too far away. And if there exists one on the right, there'll be another one on the left. But if you notice, it says occurs when y is what? So instead of limiting ourselves to x values, it looks like the y values that it's going to live in are going to be between here and here. So somewhere between y equals 0 and y equals negative 1/2. Because if it's further away than y equals negative 1/2, it's definitely further away. But it could be some random point right here. So we'll call that point x, comma y. And now we'll call the distance between them big D. Right? Yeah. So to write the equation then for the quantity we're trying to minimize, which is distance, remember it's the square root of the change in the x, which is x minus 0 squared, plus the change in the y, which is going to be y minus negative 1/2 or y plus 1/2 squared. Okay, so now we need to get that in terms of a single variable, and you could do it in terms of either variable. But notice since it's asking us to get the y coordinate and not the x coordinate, it'd be great if we can get this in terms of y instead of x, right? So what is the constraint? What's allowing us from getting right up there in 0 and negative 1's face and saying, is this close enough for you? Sorry, I lost it a little bit. You got to stay on the parabola. So the parabola itself is a constraint. And the equation of the parabola then is the equation we're going to use. So now notice I have x squared right there. So maybe I could just solve this one for x squared and get negative 2y. So that would be a nicer or an easier substitution. Negative 2y plus y plus 1/2 squared. And now I know my relevant domain, as we already mentioned, is between 0 and negative 1/2, which I guess would really be negative 1/2 and 0. So if you did it all in terms of x, that's fine, but then once you find the x value, you're going to have to translate it back to a y value. So knowing what variable you're interested in can kind of help guide how you do that. All right, so now we'll take the derivative, but here's the thing. If you take the derivative, it's going to be 1/2 times all of this to the negative 1/2, which means that's just going to jump to the bottom. So I know it's already going to be like 1/2, which will be a 2 in the bottom, all of that to the negative 1/2, so it'll be the square root of all that right there. I'm just going to put blah, blah, blah. Okay, that's not really going to be important, because remember, when we take the derivative, we want to set it equal to 0. So what's going to be in the numerator? It's going to be the chain rule stuff. It's going to be the derivative of the inside function. So let me just kind of, well, we'll do it right here. We'll put it in the numerator to begin with. So that becomes negative, we're taking the derivative with respect to y now, so it's negative 2. And instead of expanding this, I'll just use the chain rule. Plus 2 times y plus 1/2 to the first times 1. So if we set it equal to 0 now, there is the derivative. And a derivative is equal to 0 when the numerator is 0. So negative 2, if I distribute now, that's plus 2y plus 1, bless you, equals 0. Bless you, so 2y equals 1, and y would equal 1/2. Bless you. Bless you. Now, what's wrong with getting y equals 1/2? That's the only critical value. Where is y equals 1/2? It's up there. Bless you. It's not in our relevant domain, bless you. Bless you, bless you. There's a few extras if you need them. Bless you, bless you. And it's definitely, bless you, not on the parabola, bless you. So the only critical value is not relevant. Therefore, the closest point, if it's not a critical value, is going to be where? One of the endpoints, right? So let's figure out what that is. The first endpoint would be y equals 0. How far away is the point 0, negative 1/2 from the vertex? Well, you don't need anything fancy for that because it's a vertical distance. It's a half unit away. When y is negative 1/2, how far is that distance? Well, that one we need to figure out, okay? We just want to know the x value when y is negative 1/2. So if I plug that back in over here, I know that x squared is equal to negative 2 times, if I plug in the y value of negative 1/2, that gives me x squared is equal to 1. And when I take the square root, I get 1 because it's a distance. 1 would be over there, the negative would be over there. So now, which of those two numbers is smaller, 1 or 1/2? 1/2. So it turns out in this problem that the closest point was, in fact, the endpoint, and it was the vertex. So the y value of the closest point is 0. So kind of a nifty little problem, optimization. But you got a phantom critical value on that one. And the key there was to kind of do it in terms of y. And the problem set up nicely for you to do that. That's why they kind of gave it to you as x squared equals negative 2y, essentially, to encourage you to do the substitution that way. If you also remember what I told you when we did these types of problems, if you're trying to minimize the distance and the distance itself is a radical, you can work exclusively with the radicand, because making the radicand as small as possible then will make the square root of that small number as small as possible. And you can see right here why that works. If I had just taken the radicand and minimized it, it's the same thing as working with the numerator of the derivative, which is what we did anyway. So it just saves a little bit on the derivative. Okay, so that was maybe a doozy to start with, but maybe they became less doozy after that. Number 2 wasn't even a calculus question. Were there any others that y'all needed to go? 8 more or number 8? Okay. You said 8 also. Okay, well 8 it is. Yes, you may. All right, so if f of x is 2 plus the absolute value of x minus 3 for all x, what's the value of the derivative at 3? Okay, anytime you have an absolute value function, whether it's a derivative equation or an integral equation, you want to think about what the graph looks like, okay, especially for an integral equation because it's just going to be triangular regions. So if you put it into standard transformation form, it looks like that. So remember, your parent function is the V for victory graph, right? At the vertex is 0, and the minus 3 moves it 3 to the right, and the plus 2 moves it up 2 units. And it still opens up. So it looks like that. Now, here's how you can figure out the slope of the line. If you look at the coefficient of x, it's a 1 on the inside. It could also be factored out. But what's the number in front of x? 1. Okay? So that number is going to be plus or minus the slope on either side. So the slope is 1 over here and negative 1 over there. If there had been like a 2 factored out, now the slope would be 2 and negative 2, so on and so forth. So what that means then is everywhere to the right of 3, the slope is 1, so the derivative is 1. Everywhere to the left of 3, the slope is, I think I said negative 1, but I sure as heck didn't write it. There we go. Everywhere to the left of 3, the slope is negative 1. This is asking us for the slope at 3. Well, what do you know about the slope at 3? There's no slope because it's a sharp turn, right? The slope from the left does not equal the slope from the right, so this one is D and E. Now, there's a quick way to determine if you're asking for the slope at the vertex, because that value will always be the value that is the 0 of the absolute value cand. I don't even know what you call that. The thing inside the absolute value cand, like radicand, right? So if you plug in a 3, 3 minus 3 is 0, so you're approaching the V, which will be D and E. Yeah.
Okay, so I tried to take the derivative of it, and then I got none existent.
How'd you do that? How'd you take the derivative of the absolute value?
Well, you see,
Yeah.
I just got
Lucky?
I just got 1, and I was like, 3.
Yeah. It's very hard to take the derivative of the absolute values. You have to do one of two things. You either have to decompose it into a piecewise function, and then take the derivative of both pieces and realize they're not the same from both sides, or you have to use the identity, the square root of x minus 3 squared, and then you do the chain rule, okay? You want to see what that looks like? Let's try it, okay? So if that's f, then the derivative of f is going to be f prime, and 2 goes to 0. So here you're going to have to do 3 layers. You have blob to the 1/2, blob squared, and blob. So it'll be 1/2 blob to the negative 1/2, which is x minus 3 squared, times the next layer is blob squared, so it's 2 blob to the first, and then the derivative of the innermost blob is 1. What happens, though, is when you package this thing back up, you're going to have a 2 in the bottom and a 2 in the top. So actually these divide out. But when you put this back in the bottom, it becomes in the denominator now the square root of x minus 3 squared, which now goes back into this format. Okay, so it jumps into there. And then this becomes that. And speaking of jump, hola, hombre trepador. The derivative of your absolute value function is jump man. But now notice if you try to evaluate it at 3, what happens when you plug in a 3? You get 0 over 0, which is dne. The function is dne. The limit still exists, but the function is undefined. So that's how you'd have to do it. So again, anytime you have absolute value, whether it's an integral especially, because then it's just going to be little trapezoids or triangles, just graph it. Transformation of an absolute value function. Okay? Good stuff. Y'all are asking questions that the other classes did not ask. That's good. I think they were just too afraid to, because I was like this. You got any questions? Come on. Yeah. I didn't scare you? Good, good. Yeah, I really didn't do that in the other classes. I'm wondering if the other classes actually got all of these right that y'all had questions on, or if they just didn't. Certainly, where they weren't scared, because I was being facetious. I'm an unapproachable person, right? Pretty approachable. Oh, pretty approachable. Thank you. All right. What's the derivative of arc sine at the origin? And then we're going to use it to write the equation on the tangent line. Okay. So we need a point and a slope. The point is given to us implicitly. It's the origin. It's 0, 0. So all we really need is a slope and a point. That's the derivative. So what's the derivative arc sine of blob? Well, it's 1 over the square root of 1 minus blob squared. You got to memorize that. 1 over 1 minus blob squared. And then times the chain rule, the derivative of the blob. The derivative of 1/2 x is 1/2. And that's enough to miss it right there, the chain rule. Yeah, so if you simplify, you get 1 over 2 square root of 1 minus x squared fourths. And now if you plug in a 0, you get a 1/2. So now the equation of the line in Taylor form is y equals the y value 0 plus the slope 1/2 times x minus the x value. Now, if this were a free response, you wouldn't have to do anything with that, but it's a multiple choice, so you actually have to match up the answer to what they have. And if you notice, they don't have any fractions in their answers, and it looks like the x and y are on the same side. So keep that in mind. If we distribute, you get rid of 1/2 x, multiply both sides by 2. And now if you subtract the x, you get negative x plus 2y equals 0. But again, if you collect it on the other side, all the signs will be different. So if you find that you have all the signs opposite, just multiply through by -1. So it should be one of these two answers, and it's answer choice A. Okay, so it doesn't really matter. They're both the same. But, of course, they'll have just one of those two. Any other questions?
Are we going to do the free response?
Yeah, we're going to do free response. As soon as y'all quit asking so many questions.
What about that one up here, like at number 5?
Number 5, you do have another one.
This one.
Yeah, number 5 is a good one. Everyone asked about this one because this one is not a computational one. This one is a more like, what if kind of question. So you got two functions, f and g, such that the derivative of one is strictly larger than the other one, which means it goes up steeper forever more than the other one does, okay? The slope of one is always greater than the other at a particular x value. What can you say about their graphs? It's talking about intersections. So in this case, you want to like draw scenarios and try not to draw like just typical representations. You want to think outside the box. The typical representation would be this. If you let f of x be that one, and g of x then would be maybe one that is not as steep, so like this, but still positive, those intersect exactly once, right? And because they're lines, they'll never intersect again. Now, even if they were curves, okay, you could have f of x looking like this, and g of x looking, bless you, like that, not as much. They're only going to intersect once. Once they intersect, since the slope of one is bigger than the other, they'll never intersect again. And they only intersect if the one that's steeper starts below the other one. So what if you drew this? What if you thought of something like an exponential function, and you had the one that grew rapidly starting above the one that grew more slowly? Okay? Will those ever intersect? Certainly going out to the right they won't, but they also will not intersect when you go out to the left, because they're both approaching 0, and will they intersect? If you go out forever. Oh, wait. Yeah, these actually, this one, because f of x is steeper than g, it'll eventually cross g. Yeah, it'll eventually cross g. Well, yeah, this is what I'm saying. Let's think about, instead of having them both be positive, what if I do this? Now will they ever intersect? No. Because now f is a greater slope than g because it's always positive and g is always negative. These will never intersect because they're both approaching 0 from different sides. Okay? So it didn't say anything about both of them having to be positive, did they? So that's where you're thinking outside the box. So think about straight lines, think about curved lines, think about positives, negatives, fractions, 0. Those are kind of looking at all the gamut. So in this case, they can intersect once or not at all. So which answer choice lines up with that? B, right? They can intersect once, but no more than once. That also implies that they don't have to intersect. So the answer was B. So that's just kind of like drawing different scenarios. And that's kind of the easiest way to do it. All right. I guess you didn't even have to think exponential. You could have just thought a parabola opening up and a parabola opening down. Well, no, you wouldn't do that because never mind. This one would be negative and that would be positive. So they had to be monotonic. So exponentials take care of that. Yeah. All right. Sweet. All right. So let us jump then to the free response, unless there's another question. Yes. Oh, yes, you may. Yes, you may. All right. So the free response, we're going to start with the last one from the 2000 exam, number 6. It was a no calculator question. Consider the differential equation dy dx equals 3x squared. I'm just going to write it down here because I don't have any room to work it. It's 3x squared over e to the 2y. It says find the solution satisfying the initial condition f of 0 equals 1/2. So this is the type of question that on an AP exam is going to be worth 5 points, possibly 6. You're going to separate the variables. You're going to integrate both sides. You're going to put plus c. You're going to find c. And then you're going to write the particular solution. So the first step, of course, is to separate the variables. So in this case, if you multiply both sides by dx, it's not going to be enough. You're also going to have to multiply both sides by e to the 2y. So it'll divide out on the right and become e to the 2y dy. Then you have 3x squared dx. Now, kind of a word of caution here. Both sides just have one term. But if either side had more than one term, when you multiply by dy or dx, they would have to be set off in parentheses because the dx and dy are factors, and without the parentheses, they wouldn't get distributed like they should. All right, so that's going to earn a check. This one's worth 6 points, actually. Once you have that, then you integrate both sides, and that does not take away the check you've already earned. And now it's time to integrate, which is the fun part. So you have e to the blob. This is a real simple pattern recognition. You have 2y on the inside. What is the derivative of 2y? 2. We don't have a 2 out there, but if we're only off by a 2, is that okie dokie? Yeah, we just have to have a correction of a 1/2. If we're off by a 2, yeah, we have a correction of its reciprocal 1/2. And now the second part. What is 2y inside of? It's inside of the e function. What is the antiderivative of e to the blob? E to the blob. Okay, so that gives you your second check. Remember, we don't need a plus c on the y side.
And so we don't have to show that we multiplied out by
No, you don't have, this is all you have to show. On the right, it's a little easier, right? It's just x cubed. That earns the third check, and then right there, boom, plus c, there's the fourth check. So right here, you get 4 checks already out of the 6th. And hopefully you haven't broken a sweat. Hopefully on the test you won't either, because I think the gym is probably air conditioned. All right, now we got to solve for y. And remember, as we solve for y, c is the ShamWow c. It can absorb constants. So the first thing I'm going to do is multiply both sides by 2 to get rid of the half. So you get e to the 2y equals 2x cubed plus 2 times c, ShamWow c. And now we have to un-e both sides by natural logging it. And I'm not going to show that here. I'm just going to say to myself, the natural log of e to the 2y is 2y. And then on this side, I get the natural log of the quantity, 2x cubed plus c. So that's now inside the argument. And then the last thing we do is multiply both sides by a half or divide by 2. And we end up with our general solution. Yes? Right, you have to multiply both sides by -1 first, and then natural log both sides. All right, so there's the general solution, and you typically won't get a separate check for that, but it helps you get the other two. So now we use the initial condition. So you could say for f of 0 equaling 1/2, okay? When you're doing something else, you kind of make that notation, or you could say at 0, 1/2. So now we'll plug a 1/2 in for y into the general solution, and a 0 for x, which means we get that. You just earned the 5th check for using the initial condition. So the moral of that story is if you think you have the wrong equation over here, don't give up. Use the initial condition. There are generally qualifiers that you have to meet in order to still get the check. Like if you couldn't get it, you can't just make up y equals x and try it. But as long as it's still, in this case, I think a log function, even if it's wrong, like if the plus c is on the outside, you can still get the check for using the initial condition, even if it's the wrong equation. So if you divide by a half, you get 1 equals the natural log of c. If you e both sides, you get c equals 1. But you've already earned the check. You get c equals e. Sorry, e to the first. I did that hastily. Let me not do it hastily. E to the first, e to the that, e equals c. There we go. So, which is a very short transitional word, right? So, 2 letters. And then you plug that back into the general solution that you used earlier to find c. It has to be the same one. Plus e. And that, you don't have to box it, but that is your last check for this problem. So you got 6 for this. 6. So if we look at the scoring guidelines, here they are. You got 1 check for separating the variable, 1 check for each antiderivative, so check, check. 1 for the plus c, the constant of integration. And here it says 1 check for using the initial condition, and then 1 check for solving. You're pretty good, right? But hopefully this is one where you're like getting all 6 out of 6. So you would lose a point if it wasn't a log function. But look at this one down here. Here's the other note, and they always have this. Note, 0 out of 6 points if no separation of variables. So it's plus 1 if you do it, and minus 6 if you don't. Seems fair. Yeah. Okay. So with 6 points, there's only 3 left out there, and we're going to get all of them. So here's what it says next. Find the domain and range of the function that we found in part A. Oh, sweet. Okay, we could do that. Remember that there are 3 things that affect the domain of a function if it's not a piecewise. Can't divide by 0. Here's the equation. Do we have any denominators with a variable? Nope, so that's off the list. We can't take the square root, the 4th root, the 6th root, or any even root of a negative number. Do we have any square roots, 4th roots, or 6th roots? We do not, so that one's not going to matter. So maybe it's all real numbers, but there's a 3rd one. We can only take logs of what types of numbers? Positive numbers. So if you ever have a log, the way that you find the domain is you take the argument, that's the thing inside the log, 2x cubed plus e, 2x cubed plus e, and you say that it has to be strictly greater than 0. Just like we did in pre-cal. You say it's strictly greater than 0. And you get a check for that. Yay! Wow. Yes. Now, unfortunately, this is not a linear inequality. We can only solve linear inequalities algebraically. So this one we have to solve graphically. So very quickly, you could actually get the right answer if you didn't realize that. You can stumble into the right answer. But in general, like if that had been x squared, you couldn't solve it algebraically. So the graph of 2x cubed is our disco graph. It's vertically stretched by a factor of 2, and the plus e does what? Moves it up e. So it looks like this and like that. And now we want to know for what values of x is that graph positive. It's going to be positive strictly to the right of the x-intercept. Right? See that? Of the x-intercept. So let's find the x-intercept. We'll say 2x cubed plus e equals 0. And now we can solve the equation. 2x cubed equals negative e. X cubed equals negative e halves. And when I take the cube root of both sides, or raise both sides to the 1/3 power, do I need to consider plus or minus for cube roots? No. All right, so if that's the x-intercept, how I go to my graph, I want everything that's strictly to the right. So all you have to do is say the domain is, you don't even have to use set builder notation, but I'll use it. It's the set of all x such that x is strictly greater than the cube root of negative e halves. Or you could say parenthesis negative or cube root of negative e halves to infinity if you want to use interval notation. Now for the range, we'll call it r. The range is always harder to get unless you have the graph. We don't have the graph, and we don't have a graphing calculator. So here's what you do. You just say, hey, it's a log function. It's a natural log function. Every log function that I've ever worked with had a vertical asymptote, and it was monotonic increasing or decreasing on either the left or right side. But what has been the range of every log function? All real numbers, right. Yeah, negative infinity to infinity. All real numbers. Guess what this one is? All real numbers, yeah. There you go, all real numbers. So where do the checks come from? Well, you get one check for saying the inequality is greater than 0, one check for the domain, which is, notice they don't even have it in set builder notation. And the range, they went fancy with inequalities. Negative infinities, less than y is less than infinity. You can just say double bar r, right? Absolutely. Everyone knows what that set of numbers is. It's a lot faster. In fact, I would say don't do this because there's a tendency to want to do that. And is that true? It is not. You can't get to infinity. So anyway, there you go. There's all 9 points on that last one. It wasn't too bad. Any questions on that one? Fun, or fun? The latter. Good. And not too bad. So easy. It was kind of a easy one. All right. Next year, 2001. This was the 4th question on the exam and the first one without the calculator. Nowadays, the first 2 are with the calculator, and the last 4, starting with 3, are no calculator. So I need some space. So let's go ahead and get all that and put it in a space bag. And we'll put it under the bed. You know, for winter. Yeah, just space bag. All right. It's still there if I need it. There it is. See it? There's a little semblance of it. Right there. Oh, there it is. Okay. So if I need it. If it gets cold, I'll take the sweaters back out. Let h be a function defined for all x except 0. So if you recall from your experience here, if College Board is going to give you a heads up as to an interval, like sometimes it says t has to be greater than or equal to 0, or in this case, x can't be 0, it's for a very good reason. It's because that number there is probably going to come up or be important later on, and if you don't realize that, you're going to lose some points. Same thing if they had said t is greater than or equal to 0. In that case, you might come up with a negative number in your calculations, and you need to remember to discard it. So, very quickly, can x equal 0? No. All right? Such that h of 4 is negative 3. That's a handsome little initial condition. And the derivative of h is given by this. Oh my gosh. They're giving me so many things here. Oh, and by the way, x cannot be 0. Got it. Thanks for the warning, College Board. So not only is it not in the domain of the derivative, which it clearly is not, they're saying that it's not in the domain of the function. There's something going on at x equals 0, and it ain't a function value. Got it? All right. Part A. Find all the values of x, so we're looking for x values, where h has a horizontal tangent. And then determine if there's a local min, max, or neither at that point and justify. Okay, so it didn't even say to find all the critical values. Normally, critical values are where the derivative is 0 or undefined. They're telling us just to find where it's 0, right? So here's what you would show. Part A. H prime of x equals 0. When the derivative is 0, we have a horizontal tangent line. Now, the function is x squared minus 2 over x. So as long as you show h prime equals 0, that's good. You can either say it like this, or you can write the entire expression that it's equal to and say it's equal to 0. But going forward now, because h prime is a quotient, when is a quotient equal to 0? When the what 0? Numerator. Okay, so that's x squared minus 2. So I'm going to go ahead and then say x squared minus 2 equals 0, and now I'll solve. X squared equals 2, and remember when you take the square root of both sides, to remember, plus or minus, yes, plus or minus. All right, so we have two critical values. Now, to determine if they're local max or mins, we can either do the first derivative test or the second derivative test. They gave us the first derivative, so let's use the first derivative test. So we'll make a little number line chart. We got x prime and h, or x and h prime, sorry. We got negative square root of 2 there, and square root of 2 there. And what else goes into any number line besides critical values? 0. Any discontinuities, yes. Whether they're vertical asymptotes or holes or phantom discontinuities. They told us that x can't be 0, and we just found two critical values on either side of 0. We need to put 0 in the chart. If not, we're going to get burned. So if you recall, I said if you ever have a discontinuity, put it in your chart and put it as a dotted line, because that's going to be a reminder that it's a discontinuity, and therefore it will not be a local max or min. Okay? So whether it's a first derivative number line chart like this, or a second derivative one for concavity, any discontinuity along with the critical values and PIVs, they always go in the number line chart. Now feel free to choose numbers like -2, -1, 1, and 2. And if you plug them into h prime, which is given up here, let's see what we get. We get 4 minus 2 is 2 over -2 is negative. Plug in a -1, you get negative over negative, which is positive. Plug in a positive 1, you get negative over positive, which is negative. And if you plug in a 2, you get positive over positive, which is positive. So that's just filling in the number line with signs. Now, I like to do this, negative to positive and negative to positive. Because then you can visually see that at both critical values where there was a horizontal tangent, we have local what? Mins. And having the dotted line here is to prevent you from saying, at 0 there is a local max, because there is not, even though the h prime changes from positive to negative. It's not a critical value. Huh? It looks like it's winking. Yeah, this guy and this guy. All right. So now we write the sentence. H has local mins. It said to find the x value, so we don't need the actual mins. So we say at x equals. And you got to be careful here not to use -2 and 2. That's why we wrote the critical values way up here. At x equals plus or minus the square root of 2. So you can clump them together. Comma, since what? H prime changes from who to what? Negative to positive. Where? In France? At x equals positive or negative square root of 2. Good. So you do say it twice. Because you're saying here's where they occur, because that's also the place where they change signs of h prime in this fashion. Okay? And there you go. That's going to get it. Now, if you had forgotten 0, you're going to get an automatic disqualifier for not considering 0, and then you would probably not get one of the local mins, because if you just chose, let's say, -1, you would have negative, positive, positive, and you would miss the local min at square root of 2. Or if you just chose +1, you're going to see negative, negative, positive, and now you're going to miss the local min at negative square root of 2. So you would lose more than 1 point. It's that important. All right, so let's see where the points come from. You get 4 for that. You get 1 point for both, plus or minus square root of 2. So how important is it to remember plus or minus? Pretty important, right? The analysis, they used to grade the number line chart. So that's what they mean by that. They don't do that anymore. Now you have to write the sentence. So you're going to get 2 points, 1 for each correct answer. Local min at negative square root of 2, check. Positive square root of 2, check. And then the 1 point for the analysis would come from now the justification, since h prime changes from positive or negative to positive, at each of those values. So remember, for the first derivative test, you have to talk about a sign change in the first derivative. And you don't use pronouns, right? You don't say it changes signs, you say h prime changes signs. Sweet, so we got 4 points, which means we are probably above the average. Yep, yep. And there's still 3 parts to go.
Average is 3.3 something.
3.5. Sometimes it gets all the way up to like 3.8. Oof. All right. Part B. On what intervals, if any, that's mathematical foreshadowing, could be 0, is the graph of h concave up? Justify, bless you. All right. So any function is going to be concave up when its what is what? When its second derivative is positive, greater than 0. Second derivative is concavity. I have the first derivative, so I need to find the second derivative and then see where it's greater than 0. Now, to find the second derivative, you can do it one of 2 ways. You can simplify h prime first by saying x squared over x, and then minus 2 over x, and then you'll have 2 terms and you'll have a power rule. But then you'll have 2 terms in your final answer, and that's not as easy to analyze where it's positive or negative. So here's what I would recommend. Use America's favorite, Hody-High rule. It's a quotient. Hody-High, right? Hody-High. It's not the Heidi-Ho rule. It's the Hody-High rule. So start with a ho, end with a ho. Ho, d-high is 2x, minus high, d-ho is 1. All over, ho, ho. Now we do need to expand it, so we get 2x squared. And here's where the Hody-High rule can bite some people. Whenever you expand it, you're going to have to distribute something from both sides, because it's always going to be a minus there. And if d-ho is more than 1, like a 2, you're going to have to distribute now a negative 2 or a negative 3. So be careful or mindful of that. In this case, it's just a 1, so we can just distribute the negative and be fine. Negative x squared plus 2 all over x squared, and then I get x squared plus 2 over x squared. And now I want to know, for what values of x is that thing greater than 0? Guess what? For just saying greater than 0, you got to check, because you're communicating how the second derivative is related to concave up. Sweet. And now we just have to figure out the x values. Well, notice that the denominator x squared is always positive except when x is what? 0, in which case it's non-positive, it's 0. But x squared plus 2 in the top is positive when? X squared plus 2. It's always positive. It's 2 at the very least. It's only bigger. So for what values of x then is the quotient of 2 positive numbers positive? Always, except when x is 0. There it is again. Wow. So now you can say greater than 0. So h is concave up. You could say for all x not equal to 0. And if you forgot to add that little piece there, you did not get the check for that. If you want, remember, you could use this symbol for all, the upside down, capsized, capital A. Pretty neat, the real symbol, for all x not equal to 0. All right, so that was worth, let's see, we're down here. You got 3 checks for that. Wow. 1 for the second derivative, 1 for showing that it was greater than 0, and then 1 for the answer. And look, they said therefore. That's a lot of letters, right? We just write so usually. That's a lot faster. H is concave up for all x not equal to 0. So if you didn't say for x not equal to 0, you would lose 1 of the checks. So again, if they remind you at the beginning, it's for a reason. It's for a reason. And then there's one part left to go, or two parts. Wow. It's a problem that never ends. Write an equation for the tangent line for h at 4. Tangent lines. Yeah, it doesn't get easier than that. We need a point and a slope, don't we? So the point is going to be 4 comma h of 4. Now, how am I going to find h of 4 if I don't have h of x? I only have h prime of x. Yeah, I read that at the beginning, and I haven't used it yet. And I was wondering why they gave it to me, and now I'm like, oh, that's nice. They gave me the actual point. So it's the point 4 comma negative 3. And now I need the slope at the point. So notation, and what's the third one? Notation. So we need to show h prime of 4. H prime of 4. Well, they gave us h prime, so if we plug in a 4, we get 16 minus 2 is 14 over 4. And you don't have to simplify that. I'm going to call it 7 halves, just because I want to. So, instead of therefore, the equation is y equals the y value of negative 3 plus the slope of either 14/4 or 7 halves times x minus the x value of 4. And you don't have to put your line in any specific format. You don't even have to box it. Remember that the only negative in the Taylor form is the x minus. Some people want to put minus the slope, but everything else is positive. Positive y, positive slope, x minus the x value. Okay? Unless, of course, the slope and the y value are negative themselves. All right, so there's another check. It says tangent line equation, check. So the last one is worth the last check. Let's get it. Yeah, does the line that we just wrote the equation for, does it live above or below the graph to the right of 4? Below. Why? Very good. Remember, whether the tangent line lives below or above a curve depends on the curvature of the curve. Okay, if a function is concave up, the tangent lines live below, and the secant lines, by the way, would live above. But if a function is concave down, the tangent lines live above, and the secant lines would live below. And we just said on part B that the graph of h was concave up everywhere except 0. Is greater than 4 everywhere except 0, or included in that interval? Yes. So here's all we have to say. If it's concave up, the lines are below, right. So let's use the word, does it live above or below? So if it was an approximation, we would say it's an under approximation. But we didn't approximate anything, so we'll just say below, comma, since h of x is concave up for x greater than 4. You do want to speak specifically to the interval that they gave you. If you just said it's concave up for all x not equal to 0, it wouldn't be wrong, but it does hit the nail right on the head. So if they specifically say to the right of 4, just be very specific and answer it that way. That's it. So nowadays, maybe they'll ask you that, maybe not. Maybe they have you write the equation and you use it to approximate the function somewhere, h of x somewhere, and then they would ask you, is it an over and under approximation? It would be the same justification. The tangent line approximation would be an under approximation for the same reason. And that's the 9th and final check on this question. So there you go. Oh, good catch. We're done. Any questions on that? All right, what's DO do on Monday? AB01. Yeah, and we'll just keep this exact same thing going until the day before the AP exam. And I will not have any reviews on this weekend because it's a 3-day weekend. But we'll pick back up with the weekend reviews starting the weekend after. And then we'll have after-school reviews the week before the AP exam as well. So lots of review sessions still out there. People tend to do a lot better on the exam when they come to the extracurricular reviews.